The next step in the A to D conversion process is quantization. So this is the topic of section 8.3 in your textbook. Okay. So quantization. So this is the step in which our analog sample values are converted into digital values. And so I'll try to illustrate with an example waveform here. So we've got something like this. Okay. And we're going to take samples of this waveform every capital T seconds. Okay. So these would be, for example, those particular sample values. At this point, we've just assumed that whatever these samples are, it might be 3.1567889. That we're able to represent these sample values exactly. But in practice, at least in the A to D conversion process, we have to convert these sample values into corresponding digital values. And with any digital value represented by a certain number of bits, there are only a certain number of levels that can be represented. So I'm going to assume here that the input voltage x of t varies between the minimum of minus capital V and plus capital V, and then we've got capital L levels available that we're going to use to represent our quantized values. And then the standard notation, the quantization step size, is known as delta. So in this quantization process, these analog values are going to be converted into the nearest corresponding digital level. Okay. So these levels are indicated by hash marks on this axis. And each of these stems that I'm drawing now, the height of each of these stems should exactly correspond to one of the available levels. And so what's done is I'm going to assume that these values are actually rounded to the nearest level, the nearest available level. So in practice, our quantized values are represented now by these stems. So again, the notation that I'm using here, we've got L quantization levels. And delta is the quantization step size. And there is a relationship between delta and L and our maximum voltage. It's typically assumed that our voltage is symmetric between plus V and minus V. So the total range here is 2V, and then with L levels, the size of each step is just that 2V over L. And then if the rounding is done correctly, you can see that the maximum error that occurs, and there is error that's present. The error is the difference between the quantized value and the actual value of x of t at that sample instant. But if the rounding is done correctly, the error here should never be more than half a step. So delta over 2 is the maximum quantization error. Now, with binary encoding, we can use capital N bits to represent our L levels. And this is the relationship between the number of bits and the number of levels, L. So again, you're familiar with this from your previous digital classes. So with 8 bits, you can represent 256 different things. So 2 to the 8 is 256. With 10 bits, that's 1,024 different levels. As the number of bits increases, the number of levels increases, our step size will decrease, and our maximum quantization error will go down. So this is the relationship between N and L. We're often interested in finding N given L. That relationship is N is the log base 2 of L. If you don't have a log 2 function on your calculator, it's equivalent to log base 10 of L divided by log base 10 of 2. Actually, you can use any base for the log, so if you use the natural log, log base 2 is also equal to the natural log of L divided by the natural log of 2. Now, often in some calculations here, if you pick, for example, 200 levels, for example, then you're not going to get an integer result. So typically you would round up to the next largest value of n to get an integer number of bits required for the quantization. So let's look at an example problem where we'll use all of these new variables. This is problem 8.3-1, the end of the chapter, where we're interested in recording audio, and the bandwidth of the Fourier transform of the audio signal is 15 kilohertz. So this is the spectral bandwidth, and then so based on the spectral bandwidth, the Nyquist criteria gives us the required sampling rate. It's got to be greater than or equal to 2b, so 2 times b is the Nyquist rate. So we have to sample at a minimum of 30 kilohertz if we're going to recover the audio sample, the original audio signal. And so this is part A of the problem, find the Nyquist rate. And then part B is they give us the number of levels. It's 65,536 levels are used in quantization for CD audio. What's the corresponding number of bits? You may know this, but n is the log base 2 of L, and that turns out to be 16 bits. So with 2 bytes or 16 bits, we can quantize our audio signal using 65,536 different levels. The corresponding binary rate, the number of bits that we have to record then, would be for we're recording samples at a 30 kilohertz rate, and for each sample we have to record 16 bits. So the required binary rate is just n times fs, or 16 times 30. That's 480 kilobits per second. You'll also see bits/second, abbreviated as BPS, bits per second. You'll see both of these notations. In part D, they tell us that the actual sample rate that's used with CD quality audio is 44.1 kilohertz, and they ask for the corresponding binary rate. So with CD, they sample at slightly more than the Nyquist rate. This has a number of advantages. That it moves the spectral replicas farther apart, which allows us to have a smaller order low pass filter in order to remove the high frequency replicas. The corresponding binary rate is still NF, and so at this higher sampling rate we get then that CD audio has to be recorded at 705.6 kilobits per second. Actually, with CD audio, it's recorded in stereo, so we'd need to double this number again to get the actual rate at which data is recorded in CD audio.